speak remotely, please test your microphone. He's online. Okay, but yeah, you stop here, and then all the other slides are uploaded here, and they're in sequence number. If you saw the email from G, he may have to step out for a little bit. So if he has to step out, we'll just skip him and come back to him.
Perfect. Slides are here, right?
To get to the next set of slides, you to go from there.
Yeah, stop and then go there.
Yep, stop at the next one. Sasha, were you trying to share something? Hey, Rashad, we're all here. Could you verify that you're able to hear us? Could somebody else online verify that you're able to hear the microphones?
We are able to hear you.
Yeah.
Okay, thank you, Ketan. Okay, are we ready? Ready to go.
There's an echo coming.
Mute it.
One moment.
I'm just going to try if the echo is coming.
We're good.
Good afternoon. I'm going to do the chair slides. We'll go quickly through it. Go ahead. Unless I have. Okay, there's a note well. If you've not read your note well, please take a moment to read your note well and determine that once you've been here, you're agreeing to follow IETF processes and policies. We recommend masks unless you're speaking at the mic. Next slide. This is the meeting information. Click. G's done a great job. G, wave to the folks. No. It's setting all of this up along with Jeff and Kier. The document status is on the wiki. We will be moving wiki, but apparently it's a lot of work as I'm working through moving it to the community wiki. If you want to know about the move to the community wiki, come see me. Next slide. Look, we had an interim. We had CAR. That should have been the color domain. We had status report on CAR and CT. Jeff gave his discussion on the interoperability that has been adopted. We had next top discussions. The best chairs asked us about 2 years ago to try to look at Next Stop, and we're finally working down our pathway far enough to get to it. Next step. By the way, I'm assuming you all can read faster than I can talk, so if you want me to slow down and answer something, I will be glad to. Next. This is our current status. We've adopted draft IETF IDR-TS flow spec SRV6 policy. We'll probably go right into working group last call as an informational. We've adopted draft IETF BGP entropy label. Kudos to the authors for a really good IETF collaboration. We've adopted spaghetti deprecate, but we then found out, thanks to Bruno, that there was some of that information in an RFC. So we're probably going to abandon that. Thank you to those who are helping us with that. We need to chat after the meeting. What happens with the adopted draft? We're probably going to move to working group last call as soon as you're ready with 2 implementations. We adopted 2 things since, which is HAAS, the interoperability draft for CAR CT, which is draft HAAS IDR diffract, and we've tentatively adopted draft Dunbar, but there's a CANBOF on the same topic. So that's sort of in the hold position. And we've not drafted draft Wang IDR VPN prefix. You can ask me questions in the back about all of this if the mail list has not been sufficient. We're still in the adoption process for draft Dong. This is a little bit more than our current draft status, but you can find all sorts of details on the wiki. Next slide. Our major work items, I'm giving you a status because we have a little latitude this time. The DC drafts for BG auto configuration, in case you missed the message, we sent those to drop because we didn't get enough interest in the working group. We encourage the authors to go to ISE. We need any feedback if we should pick up the non-data center considerations. If we don't hear feedback, we'll go on to other major work. BGP flow spec. I really need, and again, this is the call from the chairs, I really need to talk to the FlowSpec V1 path redirect and interface set authors, as I haven't heard from you, and we either need to go on or drop those. And most of the drafts for FlowSpec, as we see coming up in the working group, should go to FlowSpec V2. We are starting to get implementations. Thanks to Gunter for some error reports. Color CT, we're going to look at draft Wang IDR CPR, and I have a little pre-hint that they're going to be asking for adoption, so we'll look at that. Next top is our next topic. We would appreciate any comments, thoughts, and other things. Another thing I need feedback for, and again, catch me in the hall or at the back, I'm about ready to engage in the cleanup drafts that are IDR drafts that are older than 10 years, just to sort of clean out our back queue. I think that's it. Jeff, this is our agenda. Jeff will start with the next presentation. Thank you.
Hello. Good day, everyone. Ketan Talaulikar, Cisco here. I wanted to present an update to this working group draft. It's one of the oldest draft, not yet 10 years, as Sue mentioned, but running close to it at 8 years. Next slide, please. So this is a BGPLS draft, and it introduces extensions for advertisement of T policies. So these could be RSVP tunnels, segment routing policies, or MPLS cross connects. In that sense, it is different from sourcing information from IGP into BGPLS, which was the in the base spec. It advertises the T policies as well as their status and some a bit more information about them. Next slide. So a quick high-level status update. While this document has been in IDEA working group, the base SR policy architecture was published as RFC 9256. Uh, the sibling draft, we could call it that way, the BGP SR policy has been sent to ISG for publication. That draft defines the controller to the router, provisioning of SR policies, while this draft does the reporting in the other direction. Over the past few years, the draft has been getting updates. Most of them, or almost all of them, are related to SR policy advertisement, and this is based on implementations which have been ongoing. Next slide, please. So since the last IETF, we had a bunch of updates which were posted, I believe, around August. And these were all based on implementation feedback. So the good part is there are implementations already done or ongoing for this draft. One of the key things was that we use separate NLRI types for each type of policy. So a separate NLRI for RSVPT tunnel, for SR policy, and so on, any other things which we may introduce in the future. The draft had some reference to IP tunnels, but it did not really cover that. So this was just in the introduction, so we have removed that. And then there are various clarification and updates for how to use the descriptor and some bits and bytes there. I'm not going to go over these in much detail. Next slide. So where are we at? So we are still getting some feedback from implementation, and more closer reviews are happening. So that's good. Thank you. Uh, we have some updates from in the IANA section based on some comments, and some more expecting to get during this week. So right after IETF, we can expect perhaps one more update. What I would like to call out for the working group is that based on whatever we have heard so far as authors, uh, everything is related to SR policy advertisement, and that gives us the impression that really the SR policy part is the only thing that is being implemented. So we wanted to get inputs or feedback if anybody has implemented the either the RSVPT or the local static cross connect types, because we do need to have implementations to progress this work. Next slide, and I believe this is the last one. So this is a proposal from the authors and to the working group. I would also send it out over the email. But given that we have some, at least a few implementations for the SR policy, we could look at perhaps splitting the draft, working group draft, into two parts, so that one of them may progress to working group last call and publication. So any inputs or feedback would be very much appreciated.
Any questions for Ketan? We have no questions in the room and nobody in the queue. Thank you, Ketan.
Yeah. So I believe it should be possible to split the working group document, right? To the question to the chairs.
It's certainly possible to split it. The work would remain adopted, I believe. What you'd probably want to do is prepare a version of the split document so we can see what it looks like. The usual challenge we have for those sorts of things is making sure that each document is whole and on its own, and make sure that it is easy to read.
Okay, sure. Yeah. Thank you.
Okay, we seem to have no questions. I'll be giving this one. So I'm Jeff Haas, and I'm presenting on behalf of the BGP Yang model authors. Next slide, please. So status, we have done a lot of work in the model in terms of updating the transport security, and have worked with the TCP Yang model authors specifically on how TCP AO is supposed to work, and also TCP MD5. That did result in some work inside the TCP-M working group to fix some issues that they had in their model, and we're one of the first users of the fixes. So as a side effect, we've removed some of the stuff from our end of the model and moved it into theirs, and we've updated the appendix to take care of that. We've done cleanup on a number of things relating to unions, courtesy of some of the netmod rules. In Yang, the order does actually matter in terms of what catches the possible options within the union. We've also done some additional work inside the policy module, specifically on matching on address families and neighbors. And we've added additional examples for matching next hops and communities. Next slide, please. So Mahesh is still running the GitHub that we're doing all of our stuff out of. Please take a look at it in case you want to open up issues or contribute. We are tracking things via issues for our lingering work items. We have cleaned up some of the regular expression type stuff, but however, we didn't finish all of it. A standing work item for the IETF Yang model, and also an item inside the OpenConfig Yang model, is how to model regular expressions against AS paths. We will be holding a side meeting this evening, Monday at 6 p.m. Enrichment 6 around the corner here. On this specific topic. We'll discuss possible options there, and if we're lucky, we come to some sort of easy consensus and perhaps move this item forward for next IETF, which will close out the major pieces of missing work. The AS override and replace AS, we've made some choices there. We invite the working group to please review this because this is a non-standard feature outside of the AS override use case for VPNs. And extended communities continue to be one of the more challenging pieces of modeling, both in terms of how to actually model route targets, but also the fact that IETF is adding new extended communities on a regular basis and making sure we can maintain this without having to issue a new RFC every single time we do it. Those of you who are following Yang modeling are invited to give this very deep scrutiny. This is a type of thing that the rest of IETF does not have as a general problem. Next slide, please. So we're mostly there. We are hoping that once we solve the regular expression issue that we have dealt with everything. There's a tiny bit of cleanup work left to be done. We're starting to see some feedback coming in from the field. Thank you, Rashad, for actually taking a look at things. And this has been 7 odd years of work. We're hoping to get to the point where we're just ready to ask for publication of the thing. So if you have interest in actually looking at the model, this is now the time to actually do it. We invite deep scrutiny, and in particular, since this module will be the basis for how a number of other VPN family type things, like the modules that come out of BES, tie into, it's also important for people working on the BES Yang modules to pay attention as well. And I believe that is all we have on this slide. Is there any questions? Anybody in the queue? Okay, we appear to have no questions. So we'll be moving on to the next presentation, which I'm also the presenter for.
The 5GH?
This will be the asset 03.
So I can't see them. Can't see.
No. You don't do that. Always here.
Ah, thank you. Thank you.
Okay, thank you. So next presentation is on deprecation of AS sets. I'm doing this work with primarily Sriram and also Warren Kumari. Next slide, please. So what's the motivation we have to talk about this topic? So it's worth taking a brief reminder that BGP4 came into being as the first interdomain protocol for carrying classless internet domain routing. And as a side effect, there's a lot of procedure that's sprinkled across 4271 and earlier 1771 dealing with topics that are less interesting these days than they used to be, specifically aggregation. So a couple of very basics over the next slides to give motivations for the following slides. Aggregation obviously is creating a less specific route from one or more specific routes. And people primarily use this these days to cause the less specific route to come into being conditionally. And providers usually want to do this for some purpose of announcing a stable destination towards the outside world. BGP's aggregation procedures are what actually defines the AS set component for AS paths as part of aggregation. It discusses the general properties of how it does that. Next slide. And the algorithm is fairly straightforward. The one that pretty much everybody on the planet implements these days is for all your contributors, find the longest common set of leading sequences. That's the sequence everybody shares. Take everything else, throw it into a set, and deduplicate the ASs in the set. And once you've actually done that, generate the minimum number of BGP segments to encode the thing on the wire. 4271 also talks about the atomic aggregate attribute, which had a lot of interesting controversy as we were specifying 4271 and cleaning up 1771. Effectively, what it's used for in 4271 is if you set atomic aggregate, you're allowed to throw away the AS set portion of an aggregate if you think it's safe. The original intent of atomic aggregate was don't make this route more specific or don't de-aggregate it. No implementation on the planet does this by default these days. It's usually done by other procedures. Next slide. So very basic example of what sets can be useful for. Assume that we have some AS10 that owns a 10/8 less specific route, and it's delegated maybe 10.128.16 to its downstream AS20. If AS20 sends its route to 10 and 10 was to use that to form an aggregate, then it would just simply, since it's the longest common path, well, it just has a AS path of 20 in here. So this is a case where aggregation can happen if there's no sets present. So what might actually happen, next slide, if you re-advertise this back around the corner? Well, so imagine that AS20 really isn't using its full set of address space and has holes on things. Maybe it's using 1/24 as an example. If it accepts the less specific route and doesn't have something internally to catch forwarded traffic for the network that it believes it owns, the /16, this can be a case where the traffic forwards back and forth to each other. Now, clearly, this doesn't happen in practice these days, but remember, 4271 and BGP in general came into being before some of these things were absolutely clear procedure-wise. For the most part, providers, when they're doing this sort of thing, are going to be generating their own aggregates. The aggregate route itself will generate the null route that's necessary to suppress any forwarding loops. But as you can see in this example, we can actually have a forwarding loop in terms of what the RIB is telling us without that more specific to catch things. Now, this example shows this can happen even without AS sets. Now, clearly with AS sets, this becomes a little more interesting. If you actually have the AS present as part of the aggregation and send it back towards the contributors, well, the contributors would just simply not consume the less specific route. And as a side effect, this type of problem should not happen. So that's the motivation for things like sets. However, sets cause us interesting problems. Next slide, please. Again, current practices, how do we avoid this actually being a problem? Well, filtering your own address space, it's common practice that if you own a set of prefixes, you're not going to accept more specifics for your own networks from the outside world. That can lead to route hijacks as an example. The trick is, well, policy is very easy for that. Not consuming less specific routes from the outside world is very difficult to do in BGP policy. So the practice everybody has is if you don't form, an aggregate or something else internally to catch all of the traffic, you'll do something like null route the traffic internally. Aggregation is normally how this operates, but there are other techniques. And if you do these things, the actual forwarding loops are covered. Next slide, please. Now, the question is, why do we actually even care about any of this? Why do we care about AS sets? Well, BGP security features have pushed us down the path where this is now important. Route origin validation needs a deterministic origin AS for route origin authorization records. And the problem with an AS set is it's ambiguous who the actual origin is in those circumstances. So it's recommended in 6472, don't do this. We want something to be canonical for route origin validation. It also makes things like policy very challenging. Nobody's policy engine on the planet right now that I'm aware of actually can match on sets, and this makes things very annoying. And Warren's over here shaking his head. It's like, this makes my life difficult. Let's not do this. So this is, I don't like it rather than a security feature. And the last piece is that for BGP sec purposes, BGP sec needs to have sequences to do its signatures over. So that's a further motivation, one step stronger than AS sets. There's BGP sec procedures for confederations as well. Now, the useful thing is sets are not common. A few years ago when this document was originally authored, there was 300 of them floating around the internet. There's significantly fewer, largely as motivated by BGP, not BGP sec, but RPKI origin validation is just simply causing these things to go out of existence. Your stuff won't validate with them. That said, aggregation still remains quite common. We see on about 10% of the routing table at internet, the aggregator attribute that suggests that aggregation is being done. Next slide, please. So what are we asking to be changed here? Number one, you should do treatise withdrawal. Basically, if you're going to accept them at all, don't propagate them, probably don't even use them. This is a change from the must in the prior version of the document, simply because there are going to be circumstances where people do need to do this, and we can't break all the implementations we've been shipping for 25 years. That said, you should not create sets when you do that. And this is where we need most of the normative text changes versus 4271. There's been procedure for years called brief aggregation, where you simply throw the set away and set the atomic aggregate. Brief aggregation was not well described inside the core BGP RFC. This document tries to actually clarify what actual practice is at the moment. But more importantly, it actually recommends that that's not good enough, because brief aggregation simply truncates the sets. You may still end up with a non-deterministic origin AS in some circumstances. So the recommendation of this document that requires deep scrutiny from the working group is it okay to simply make the truncation at typically the point of aggregation? That's probably going to work out fine. It'll give you a consistent origin AS for BGP security purposes. And yes, we're just going to keep putting atomic aggregate on it. Next slide. Do we actually care about confederation AS sets? Well, origin validation, as I mentioned, does not care about it. BGP sec does. But even BGP sec gives some discussion in its security section that you're going to throw away all the signatures done on BGP sec confed segments outside the confederation anyway. So it depends on your zone of trust. So this becomes less of a critical thing and more as a good idea. As part of 09, I thought maybe we can probably get rid of confederation procedures, and Sriram reminded me after publication, well, BGP sec really does strongly recommend this. So we're going to return the confed sets as a should not generate, but again, it's less critical than the AS set for global internet purposes. Next slide. So what's next? Continue to refine the 4271 text. When I was presenting this to John Scudder and Tony Lee, Tony being one of the original authors of the BGP spec in the first place, is like, well, this is obvious procedure, just throw out all this text. It's like, hey guys, it's clear that you haven't been dealing with interop labs for the last 20 years. If we just simply throw this text away without having clean procedure to do so, we're going to end up with our conformance testers filing a bunch of bugs with us. So we do need to take some care here. So we will need some deep scrutiny on this. But more importantly, what we need to do is get vendors to start implementing the new aggregation procedure for AS paths to help origin validation be more stable. That's the presentation. I see that Randy Bush is in queue.
Thanks, Jeff. Of the 300 odd aggregates in the current global routing table, you'll find that almost all of them are singletons. In other words, in an MRT dump, left curly brace, single AS, right curly brace. They're dumb. Some years back, we studied the longitudinal use of AS sets and found that most of them were pretty ephemeral. They were there for a week, a couple weeks, and then gone. I don't think there's any damage to actually just removing them. And
Thank you, Randy. Next speaker in queue, which is not Joe, but somebody behind him.
It is Joe.
Oh, okay. Thank you.
Job Snyders, Fastly. A number of years ago, operators managed to get rid of private ASNs in the default free zone by popularizing certain filters that operators would copy paste into their devices. And the purpose of this exercise was to promote some attribution capabilities. And there's an analogy to the current situation where some might argue like, hey, we see these low hundreds of routes in the default free zone and we cannot get rid of it. It will never happen. And I would beg to differ. What made it possible to get rid of private ASNs in the default free zone was that it was easy to configure this on eBGP routers connected to the internet. And as far as I know, like you mentioned in your slide that it's not easy to match on AS set segments in the AS path attribute. And I concur. It's not trivial on platforms commonly deployed, except OpenBGPD. And I want to encourage BGP implementers to make a simple button to just reject all routes that have AS sets in them. And if those buttons become available, operators will start using them and we will prune AS set routes from the default free zone. So the to-do list should be expanded by another item. Please make a knob to make it easy to reject routes that contain AS sets, and that will actually help finalize this project.
And speaking as one of the developers for one of those stacks, that is part of the queue of work to be done is supporting this.
Thank you so much.
Hi, Alvaro Rotana, FutureWay Technologies. I like this work. I was happy that you're deprecating AS sets and AS confed sets. And the document says you're deprecating, it also says you're obsoleting, but in reality, you're not. Right? You're just really saying, really don't use these. In fact, you're actually saying should not be generated, which means that people can still send them. And people who receive them can still receive them because you're saying you should treat as withdrawal, whatever you said there. In other words, we may see these forever. And I understand that there's some backwards compatibility issues and things like that. What I would like you to do is to clarify the language a little bit. I mean, if we're obsoleting, we should obsolete. If we're not obsoleting, then please say in the text, we're not obsoleting, we're just strongly recommending that these are not used or something like that, so that it's clear to people what the draft is really
right. And a big portion of the reason I got involved in this draft is the original proposal was outright obsolete. You don't want people to have their peering sessions drop because they receive one of these things coming in. So we have to deal with the fact that this is BGP. We have stacks that have implementations that have been around for 20 years. Somebody's got ancient Protean box lying around on their network. We don't want them to knock over. Okay, no further questions. Next present.
One last comment, K. Patel, Arcus. I just quickly skipped through the draft. Pretty much there. It would probably be helpful if you put in some text about forwarding loops and what can happen and what cannot.
Okay, thank you.
And I lost the server connection.
You have no problems. Oh, I lost my VPN.
That explains it.
Worst case, share from your laptop.
Extension for 5G.
Linda, I think you're up.
Thank you. So I'm just making it very short presentation on this. Next slide, please. Next slide. Okay, so this is actually a special scenario which we're going to be covered in the CAN, Computing Aware Network Involved, which is happening right after IDR. I hope people can go there if you have questions and comments. So it's really about in a small domain, like in 3GPP, they call it local data network, where the service instances are instantiated, multiple services, multiple instances. So for one service, so you could have one address have multiple instances created, and is for the edge router, the egress router, be able to propagate the properties of attached site. For example, at one particular site, you may have some kind of, we call it a site index, site capacity index. It could represent all the NRIs that reside in the site, like maybe a floor or building, like they lose power, and allow the egress router to tell the ingress router that, hey, everything associated with this particular site is capacity is down to 0 or down to 50%. So this is in the IBGP domain. Both ingress and egress router belong to the same operator. Next slide, please. So interaction to the BGP is really, we want to make those service, we call it edge service metadata, to impact the BGP decision, not going to the FIB. So those information will be integrated with long chain of factors in determining the best route. Next. So here, just an example, like BGP, you have many attributes, many policies, the different priorities, and here we got an extra service metadata, service metadata value. How do we insert that into a chain of decision point, where to insert it, so that you can integrate with the other attributes to create the best path. Next slide, please. So the main purpose of this presentation is really want to introduce a different, have a different meaning of next hop. As our IDR chair has presented that there are many drafts, the different attributes of next hop. And this is a special circumstance because this next hop, like for example, capacity doesn't really represent the next hop. The router's capacity is really represent the attached site capacity. And also those are not aggregating or forwarding the NRI received from other routers. This is really directly attached sites. It's more like a exit points egress router to the devices in the IBGP domain. So that this particular next hop can be the next hop for other attributes as well, like other routes as well. In the traditional BGP domain that you have, like this next router, next hop have some issues will impact every route which has this node declared as the next hop. But for this circumstance, this attributes only impact the service instances directly attached. So for this Anycast, for this kind of special environment, we need to have a different terms, so make it easier in IDR discussion in the future. Say you have next hop transit, which is like ASBR for the other domains. And this particular one is really the IBGP exit point. So want to differentiate that. Next page, please. So here in this draft, we're proposing a new pass attribute to represent the service metadata. This particular pass attribute can impact multiple NLIs. This has details is described in the draft. If you have any comments or any suggestions, please talk to me at the hallway or on the mailing list. Next page. This is just rehab of some of the sub-TOVs can be carried by this pass attribute. Next page, please. So today's presentation is really soliciting more comments to the draft and also asking the IDR, the community, can we create a different names for this particular next hop? So make it easier for discussion and for defining for the future extensions. We want to have like next hop transit. For this particular case is next hop BGP exit point. Thank you.
AC Lind of Cisco. I think this attribute doesn't affect the packing any differently from any other attribute at a high level. I don't see why we need to rename the next hop just to create or come up with something different. And the next hop is a required attribute. So it seems much more invasive than it needs to be.
Okay, so the reason I'm asking for that is simply because lots of drafts associated with next hop, you can propagate the NLIs received from next domain and propagate down. This is really
so you want to encode it differently too. You want to say you have to have a next hop, but it has to be of this type.
We want to differentiate the next hop, which represent the transit node versus this is just the endpoint.
Right. Without saying that I'm supporting this, you could just associate this different behavior with this new attribute you have, rather than trying to define a new next hop type. That's what I'm saying. I mean, it would be, it'd be like I'm saying, it would, next hop is required. You're saying, okay, it's required, but you can have this type or this type. It's a bigger change to BGP. That's all I'm saying.
Okay, maybe I'll find descriptors to say this is particular next hop we are talking about. Just, okay. Thank you for the input. Any other questions?
Thank you.
Okay, thank you very much. I hope you guys can come to the camp off after this. Enrichment 4.
Policy extensions. Is this G?
Yes.
Or K?
Is he G?
Hello, can you hear me?
Sorry. Please continue.
Okay. Hello.
We can hear you. And we've lost the speaker.
Hello, can you hear me?
We can hear you.
Okay. My topic is the BGP.
We've lost your microphone again.
Can you hear me? Please turn to the next page. Okay, as we know, BGP can use to propagate the as a policy candidate path to the head-end nodes in the net as a policy encoding structure. Okay. But in some cases, the VPN router needs to choose the next hop according to the IGP metric of each as a policy. For example, in this scenario, on PE1, the VPN routers to CE2 has two different next hop, PE3 and PE4. Each have one. Both as a policies satisfy.
Shall we ask G to present? G, do you want to present?
Okay, hello everyone. This is Jiedong. I will present on behalf of my colleague. Okay, this is about the motivation problem statement, because for different VPN routes, if there are different as policies available in the network to different PEs, the VPN routes may need to choose the next hop and the as a policy according to the IGP metric of the as a policy. And this figure just gives an example. Okay.
Whoops. His laptop kicked it off. Reshare. Hello.
No, I lost the.
Let me reshare. So we're on policy extensions.
Okay, let me continue. Okay, so in the example showing this picture, on PE1, VPN routes to the CE2 have different next hops, PE3 and PE4. And for each next hop, there is one SR policy, policy 1 and SR policy 2. Both SR policies satisfy the delay and bandwidth constraints, and they are candidate for to be used for this VPN route. And according to the IGP metric, there have different IGP metric to reach the different PE nodes following these SR policies. For example, for the first one, the SR policy 1, the path from P1 through P1 to P3, the cost is of the IGP is 20. Where for the second SR policy, the IGP metric for the actual path will be 120. So in this case, P1 would prefer to choose the next hop according to the IGP metric and use the SR policy 1 for the packet forwarding. In this case, the network controller will need to deliver the IGP metric of the SR policies when it advertises as a policy to the ingress node. Okay, next please. So here is a proposed extension. Basically, we propose to add a metric sub-TLV to the BGP SR policy so that it will be used as a sub-TLV of the segment list, as shown in this diagram. Okay, next page. Okay, here is the format of the metric sub-TLV, and the type is to be defined and allocated by Diana. The length of this TLV is 6 octet. There's one flag field, but none of them are defined in this version. For the metric types, there's one octet field to identify the type of the metric used for this metric sub-TLV. And on the right side, we list several code points for the metric types, including the IGP metric, the minimum unidirectional link delay, and the T metric, and also the hop count, which can be used as a metric for the SR policy path selection. And the metric value is a 4 octet value to indicate the metric of the path computed going through the SR policy. Okay, next page. So this is the procedure of the metric, using of the metric for the path selection. So in this case, the next hop to P3 from P1, we use SR policy 1 is an IGP metric 20, and for SR policy 2, the metric is 120. In this case, as a P1, we choose the next hop according to the IGP metric carried in the SR policy, and the result next hop will be the P3. Next slide, please. So when the SR policy hand and node gets a policy segment list with a metric, so it will process metric. How to process the metric is a local policy. The candidate, active candidate paths of the SR policy may have several segment lists, and each segment list may have different metric. So in this document, we recommend that the segment list in one candidate path to have the same metric type. And if the metric value of the different segment lists are different, the candidate path can use the maximum value as metric of the candidate path. And for the SR policy, it can use the metric value of the active candidate path. So we have this SR policy metric be used in the route selection. Okay, next slide. Okay, this, here are the updates comparing to the previous version. We add some metric types like the minimal unidirectional link delay metric type, and also the code points for different metric types, which are aligned with the other metric type documents. Also, there are some text about the candidate path metric calculation, as we described in the previous slides. Okay, next page. Okay, for next steps, we would welcome further comments and questions. And since it's a very straightforward document, we'd like to consider to get it adopted by the working group. Okay, comments?
You have a question from Ketan online.
Okay.
Hi, Ji. Thanks for the draft. A question, why not have the metric at the candidate path level? Because that's what's going to be used anyway. Is there a value in doing it per segment list?
Yeah, actually, here the metric of the path is to follow the actual metric of the computed path. So it is possible that for different segment lists, the metric can be different. So that's why we have proposed to have a different, a separate metric for separate segment list. And for the candidate path, you can choose the maximum value of the metric of the candidate segment list.
Right, I agree with you. My question was for the use case that you mentioned, it will be only at the candidate path level, right? So do you have a use case or requirement in mind why we need to do it on a per candidate path? I'm just referring to the use case in the draft that you just described.
Yeah, in the use case, there's just maybe just one segment list in the candidate path. But when you have multiple segment lists, it is possible you ingress node may need to know all these metrics so that you can get the actual metric for the candy pass, and maybe that is you give more information to the ingress to make the decision.
Okay, I think we can discuss offline. Thank you.
Okay, sure.
Do we have any further questions? So while we're waiting on the queue, Ji, have you actually had discussion in spring about this document?
Actually, not yet. But actually, we see that metric information have been distributed from the devices to the controller via BGPRS in the draft that Kevin presented in the beginning. So we think for the asset policy distribution from the controller to the node, that this information will be also needed. Yeah.
Okay. So we'd encourage you to take this spring to discuss. We see that Gian has joined the microphone queue. Gian?
Yes, I was going to ask the question, I guess, Jeffrey, you had asked whether this had been taken to the spring working group for feedback.
I cannot hear you clearly. Please.
Can you hear me?
Be louder.
You're very quiet.
Can you hear me? Yes, what I was saying was, I was actually about to ask the same question that Jeff was asking, whether this has been taken to the spring working group.
His question was,
Can you hear me?
Same question.
Okay, I think we can bring it to spring for some discussion. Yeah.
Anything else, Gian? Okay, I think that's this presentation. Okay. Okay, Gian, this is your presentation. And we're going to have to ask you to speak as close to your microphone as possible. You are running a little quiet. Also, we do not currently hear you.
We still don't hear you.
Okay, Gian is unshared. Make sure he's still connected.
Is there?
So Gian, you've unshared your microphone. Please reshare and see if that works.
Can you hear me?
We can hear you now.
Okay, thank you. All right. Hi, my name is Dion Mishra. I'm with Verizon, and I will be presenting this draft on behalf of co-authors. Next slide. So the motivation behind this draft, so an IETF standard exists today for connecting IPv6 islands over an IPv4 core. However, standard does not exist for connecting IPv4 islands over an IPv6 core. So this draft provides a specification of connecting IPv4 islands over an IPv6 core. As an operator migrates to a single protocol IPv6 only core per RFC 5565 software mesh framework, which involves a 6 to 4 tunnel, IPv6 packets over an IPv4 called 6P, and now with this draft, 4 to 6 tunnel IPv4 packets over IPv6 core, now called 4P. The name 6P term is defined for tunneling IPv6 labeled packets over an IPv4 core, and now with this draft, 4P is termed to define tunneling of IPv4 labeled packets over an IPv6 core. Next slide. So in this design, the 4P routers, they exchange IPv4 reachability transparently tunneled over an IPv4 core using multi-protocol BGP, using BGP next hop field to convey the IPv6 address of the 4P router so that they dynamically establish tunnels. The IPv6 signaled MPLS LSP can be utilized without explicit tunnel configuration. So basically, this is signaling the topmost label for the loopback fact label binding. 4P uses RFC 8950 for the 6 or 32 byte next hop encoding for the labeled unicast. The ingress P and egress P routers bind the label to all IPv4 prefixes per RFC 8277 BGPLU. This is for the service label bottom of stack, creating a 2-level label stack. 4P supports explicit null signaling for diff serve pipe mode. And then 4P design is also extensible to support all NRAS options. NRAS option A, B, C, and AB. 4P design is also extensible to support newer technologies such as segment routing. So it supports MPLS that exists today, as well as newer technologies such as SRMPLS, as well as SRv6. Thank you. Next slide. So this diagram here depicts 6PE RFC 4798. So here what happens is you have the transport label is first signaled from the ingress 6PE router to the egress 6PE router. And this is just the topmost label transport fact label binding to the egress PE. And then the service label, bottom of stack label, BGPL uses SAFI4 for the label binding for all IPv6 prefixes tunneled over an IPv4 LSP. Next slide. So now with 4PE, we're connecting IPv4 islands over an IPv6 MPLS core. So here, what we're doing, similarly, the 4PE routers, the ingress PE router to the egress PE router, we're signaling an LSP to the egress PE router, loopback fact label binding for the transport label. And then the service label, bottom of stack label, we're using BGPLU SAFI4 label, creating a label binding for all the IPv4 prefixes tunneled over the IPv6 LSP. Next slide.
Reminder, you have 1 more minute.
Okay, thanks. So this draft is extensible to SR MPLS. So with segment routing, what happens is the egress P signals the ingress P with a VPN color, and the VPN color is mapped to an SR policy color to intent mapping, and then the path is instantiated to the prefix SID of the egress PE. And then at the service layer, BGPLU SAFI4, all the V4 prefixes are labeled and tunneled across the IPv6 LSP. Next slide. This draft is also extensible to SRv6, and with SRv6, similar to the SRMPLS, we have the color to intent mapping that happens, where the egress P signals the color for per destination color, or per flow can also is also supported from egress P to ingress P, color to intent mapping, and then the LSP is built to the egress P node SID. As well, we had at the service layer, the RFC 9272 BGP service SID BGP prefix attribute is encoded in the SRv6 L3 service TLV function and arguments encoded into the function field. So section 3 of RFC 9252. This is also described in the SRv6 programming RFC 986 section 4.7 NDT4. Next slide. I'd like to flip to the last slide.
Last slide, thank you.
So Thank you. I would like to request feedback from the work group, and then I would like to request. I think the draft is fairly straightforward. It follows the 6P architecture, but is extensible as well to SRMPLS and SRv6. So I'd like to get some comments from the work group, and then queue up for possible work group adoption. Thank you.
Thank you again. We're over time, unfortunately, so we're going to be proceeding to the next presentation.
Okay, thanks.
Actually, this one was being presented by Ji, who is currently out of room attending a different session for a moment. So I'll be skipping to the next presentation and returning. Wei Cheng?
Hello? Do you hear me? Hello?
Wei Cheng, we can hear you.
Okay. So, thank you, Chair. I will present this very simple draft. In this draft, we hope to introduce some potential risks caused by redirection mechanism which have been deployed in operators networks. Next page. So as you know, networks currently become more complex and the traffic burst is more heavy. That may cause some network performance issue. In order to solve those problems, operators rely on some automated traffic optimization tools, which often use the redirection mechanism, such as BGP flow spike. Here, we would like to describe some risks of the redirections, which may be caused by misconfiguration, network adjust, network failure, or some other factors. Those may be caused by manual operation or caused by automated tools. So let's see those risks. Next page. So here is an example topology. There is one campus network due home to two carrier networks. The both ISP networks are multi AS domains and interconnected each other. The example traffic is between user and the server. The normal traffic will traverse through the both ISP network. So next page. So the first potential risk is the traffic detour and exposure. So some misconfiguration may cause the traffic is directed from AS 65-104 to AS 65-500. Then the value-free principle may be violated, and the traffic in provider's network will be misdirected to the customer network, which will cause detours and exposure. Next page. So the second potential risk is a black hole. So similar with the risk one, if some misconfiguration happen, that will cause the traffic is directed, such as from the 65104 to AS 500. And the AS 6500 may not be have a rotate to the destination server. Then the traffic will be discussed. That will result in a traffic black hole. The next page. And the third potential risk is the traffic loop. Let's see the orange traffic line. Due to some misconfiguration, traffic may be redirected from AS 6503 to AS 65500. And the AS 6500 learns the routing to server from AS 6. Protocols. AS 6500 will send packets back to the AS 6503. Then the traffic loop will occurs. So next page. And then the last potential risk is operation and maintenance risk. So the traffic redirection may cause inconsistency between the control plane and the forwarding plane. So if the network operation and maintain control system doesn't get the traffic redirection information in the network, some unpredictable risk will occur during the traffic optimization. So, in summary, because the networks become more complex, the redirection mechanism often are used. As mentioned above, the mechanism of the redirection maybe leads some risks. So from an operator's perspective, it's not sufficient to rely on the traditional way, some operation rules to avoid those risks. Maybe it's necessary to explore some new technical solutions, such as redirection configuration verification tools, or some protocol extension to sync up the forwarding plane and control plane, or some path virtualization tools to reduce those risks mentioned in this draft. This draft have not give some direct solutions, but one hand, the redirection in IETF can contribute something on that to help operators to solve those issues. So next page. Oh, that's all. And any question or comments?
So while we're waiting for questions, what is your intention for the future of this document?
In fact, from my point of view, we found some risks, and this moment we have not explored the solutions. We hope the peoples here can consider those problems and provide some solutions or provide some ideas in the future.
Okay, I would suggest that this might be better work for the GROW working group. So I'd encourage you to also solicit, your presentation there at some point. AC Lindham's at the microphone. AC?
AC Lindham Cisco Systems. I just had one comment here, and I've talked to some people about this. It seems almost to imply, and it's like the big elephant in the room with FlowSpec, that it's being used not for its original purpose, but now it's being used as sort of like an open flow, and people are using it for their routing mechanism instead. And I think that, needs to kind of come out if that's the intention, and this does a good by addressing the redirection as if it were. Maybe I've just missed it, but it appears to me that this is happening, and I'm wondering to what extent it has, and how many people are, if anybody, how many people are deploying controllers that use this as a open flow type protocol.
So thank you. I think open flow may be often used in a data center network. I did not have some count use open flow in such as router-based WAN network.
Okay, hopefully we'll have additional discussion on the mailing list. AC, would you please repeat your comment there, maybe to start conversation about the sort of traffic steering use case that's obviously popping up.
Okay, thank you, bye-bye.
Thank you, YJ. Next is Ji.
Thank you. Okay, hello everyone. This is Jidong. I'm going to give a presentation about the draft BGP flow spec for IETF network slice traffic steering on behalf of the co-authors here. Okay, next slide, please. Okay, a little bit about the background. We know that BGP flow spec provides a mechanism to distribute the flow specifications and the flow forwarding actions to be performed to match the traffic. And in the context of IETF network slicing, the network slice traffic needs to be steered into an NRP to meet the connectivity and also the performance requirements. As defined in the IETF network slice framework draft, an NRP is a collection of network resources in the underlying network. And in the data packet, an NRP can be identified using either the resource-aware SRCs or the dedicated NRP ID in the packet. So this document defines the BGP flow spec extensions for steering the IETF network slice traffic into the corresponding NRP. Okay, next page, please. Firstly, we're talking about the matching rules for the network slice traffic. Basically, all the existing flow spec components can be reused to match the network slice service traffic. These components are defined in the RFC 8955 and 8956. And in some other scenarios, the packet may already be encapsulated with an NRP ID. In this case, the ingress node may need a new flow spec components to match the NRP ID in the packet. And the format of the NRP ID component is shown in this figure. Um, this component encoding aligns with the specification in FlowSpec version 2. And in the flags field, one flag is defined in the current version. The G flag, which is used to indicate whether the NRP ID is globally unique or is like a domain significant. And the 4-octet identifier of the NRP is also carried in this component. Okay, next slide. And regarding the network slice traffic steering actions, basically the traffic of a network slice can be steered into NRP and then be forwarded using two approaches. The first one is we can use a shortest path within the NRP. And in the second approach is we can use a traffic engineered or TE path associated with NRP. And for the first case, if we want to steer the traffic to a shortest path, or call it BE path within the NRP, we can use two approaches. If the resource-aware segments are used for the NRP-specific traffic forwarding, then the redirect to IP action can be used to carry the resource-aware SRCs of the egress node. And if the data plane NRP ID is carried in the packet for the NRP-specific forwarding, then a new encapsulated NRP ID action is defined in this document, and format is shown in the following figure. And here, the NRP ID is carried in this action, and the flag called E flag is used to indicate whether the NRP ID should be encapsulated in the outer IP header, or whether it should be used to replace an existing NRP ID in the packet. Okay, next slide, please. For the second case, if we want to steer the traffic to an NRP-specific TE path, we can use the mechanism to steer the traffic to an SR policy, which is associated with the NRP. And similarly, we have two approaches to associate the SR policy with NRP. Either we can use NRP-specific resource-aware segments to build the SR policy seed list, or we can associate the SR policy with a data plane NRP ID. And in both of the above cases, IETF network slice traffic can be steered into the NRP T path based on the mechanism defined in the draft TS FlowSpec SR policy. And we don't need additional extensions for this NRP T path traffic steering case. Okay, next slide. Okay, since this is the first time we present this work, we would like to collect the feedbacks and comments so that we can revise the document accordingly. Thanks. Comments?
Any questions online? Okay, nobody is in the queue. Thank you, Jin.
Thank you.
Next up is Huaymo.
Hello, everyone. Today I'm going to present BGP extension for mirror banding. Next page. BGP has been extended to distribute the SR policy, basically SR path with banding to a network node. So banding here means a banding seed associated with a list of seeds. So this list of seeds defined in another path segments. For example, in this network topology, we have SR path from ingress nodes P1 to P1 to node N, and then through a green path segment to P3, P6, and then to egress node P4. So here we have a banding, which is that we have a banding seed, B seed, associated with a list of segments, which is S1 and S2. This S1, S2 defines green path segments. So when BGP sends binding to node N, which is a B seed with segment list S1, S2, in normal operation, when node N receives a package with binding seed, so node N will replace this binding seed with the list of seeds, which is S1 and S2. So this S1, S2 define the green path segment. Node N will send the package along this green path segment towards destination PE4. So in addition to that, so here BGP is intended to send a binding with a node ID of N to the adjacent node of node N. So after this, when node N fails, the adjacent node can provide protection, fast protection for the failure of node N. So here, when node N fails, P1 will detect the failure. P1, because P1 have information for binding and also node ID of node N. So P1 will replace the binding seed with the seed list for that green path segment, and then forward a package along that green path segment to P3 and then P6 and towards destination. So next page. So right now, BGP has extended to distribute routing policy through tunnel in-cap attributes. So here, we just define a sub-TLV called binding protection sub-TLV. Basically, this sub-TLV just contains the node ID of that node N something. So when BGP distribute binding, which is encoded by the binding seed and the segment list to a node N, BGP will also distribute this binding plus that ID of node N to the adjacent node of that node N. So the adjacent node can provide protections of the failure of that node N for the binding. Next page. So the extension is very simple. We just define a binding protection sub-TLV. Basically, this binding protection sub-TLV contains some flags and then node ID sub-TLV. So this node ID sub-TLV in BGP, we just use the BGP ID. So which contains BGP node ID. So next page. So we would like to welcome comments and suggestions for this idea.
I actually forgot to use the app to jump in the queue, so sorry about that. Andrew Stone, Nokia. I actually didn't read this draft, but I read the one in the PC working group, and obviously it's very similar. I just had a general question that wasn't clear to me. When you program to the neighboring routers, are you informing the neighboring routers of the entire SID list that the binding SID is being programmed with?
No, just so basically we just need necessary information, just the binding plus the ID of that protected node. We don't need the actual information.
So what I was wondering was, so if I was to use this example, so if P1 is protecting node N, and for that binding SID, how does it know that that binding SID is terminating on P6?
Oh, you mean the P1?
Yeah, so if P1 is protecting N, how does it know that it needs to reroute to P6?
Oh, that's a good idea. Yeah, that's a good question. In fact, P1 has the whole path information, right? So basically, when node P1 receives a package, and then that package will contain the segment list. So that list will contain binding seed, and then
that blue.
Also the blue one to the destination.
But the blue one could be in a local adjacency SID. So it actually,
yeah, that's right. The blue one, but that one, that local adjacency is also included in the segment routing header, right?
But that blue label, for example, if it's MPLS, that blue label is local to that P6.
Yeah, that's
So
right.
P1 doesn't know which router is advertising that blue label.
That doesn't matter. So P1 only cares those green ones. So first the P1 just replace the binding seed with those seed list for green one, right? And then so P1 has the whole segment list, and then P1 will just get rid of the seed for that failed node, and then go to the next hop. That's all, right? The next one he doesn't care.
I do think there's a gap here. I can follow it up on the list.
Yeah, we can go discuss details.
And then one other detail just to kind of throw in the mix. The actual label stack of the binding SID could also have nested binding SIDs. So in that case, you're even further down the chain of trying to understand where do you pop out on the other end of the binding SID. So for example, it could be P6, it could be P5, P3, P whatever, but you don't actually, from the perspective of P1, you don't know, because now you're talking about a neighbor of a neighbor potentially.
Yeah, basically, the idea is that as long as we have those binding seed is labeled seed, but then we will check the next hop, even so is the adjacent seed, and then we know that the adjacent will have next hop, and then we figure out that next hop, right?
Okay.
We have that information.
I'll send the list.
Yeah, we can discuss in detail in the list. Okay.
Any further questions online? No questions. Thank you, Raimo.
Thank you.
Okay, so this draft is about extending or derive an extended community from a route target. I want to talk about a general example use case first. Let's say you have a VPN with 10 PEs or 100 PEs. And for that VPN, we have a route target. We call it RT1. The route target, it is an extended community, say EC1, with a subtype 0x2. In this case, RT1 and EC1, they are the same thing. But when we say a route target, we emphasize that it is an extended community for a purpose that is used to control the propagation and importation of the routes. In this case, routes with RT1 will be propagated to and imported by all those 10 Ps of the VPN. But when we only say extended community, we do not imply that semantics that for the route propagation and importation. Now, let's say that we need to send the one route to PE only. And we want to say that this route is related for that VPN. So to control the route that to be propagated to PE1 only, we want to use a different route targets. We say RT2. And to tell the PE1 that this route is related to this VPN, we attach a different extended community for that purpose. So in this case, RT2 cannot be the same as RT1 because RT1 will get the routes to all the PEs. Here we want to direct the route only to PE1. The EC2 is to indicate that this is for the VPN. So the EC2 and RT2, they're also different. So to indicate that this route is for the VPN, even though RT1 has the implied semantics that it is for this VPN, we cannot use RT1 here either. Then the EC2 can be an arbitrary extended community configured for that purpose, saying that this is related to a VPN, but it would be nice if we can just derive the EC2 from RT1. Next slide. So this is what is about here. For any RT, we can derive a corresponding extended community simply by changing the subtype of the RT to a new value. So also, based on the new value for the subtype, if we change it back to 0x02, which indicates the RT, then we get the original RT back. So, and we actually have got a subtype 0x15 assigned for this purpose. So if you have a RT, which is subtype 0x2, you should simply change the subtype to 0x15, you get an extended community corresponding to that route target. Next slide, please. So we have documented the 3 specific example use cases that relate to this general use case. I'm not going to go through those specific use cases here, but this is one example in eVPN. We could use it this way, but we don't have to. Next slide, please. There are 2 other example use cases documented in that draft. In fact, just before this IDR meeting, a few of us were talking about another specific use case. Again, it's related to the general use case. So general use case is that giving an RT derive extended community and use it for whatever purpose you want to use for. Next slide. So this document only specifies the derivation of this extended community from a route target by using this new 0x15 subtype. We do not specify how it will be used. It can be very creative, whatever use case you may have. It is a simple idea. The co-authors here, we believe it's ready for the working group adoption. So, comments?
Questions, comments online?
AC Lindum, I just got one question. Would you still need to document in an IETF, an IDR draft, the specific usage, like you have these 3? You still would. This would just make the assignment automatic, right? From RT's existing for the VERF.
The assignment.
I mean, not for the VERF, the RT, and you have an existing RT and you want to derive it for a use case. That use case would still have to be documented in a draft, wouldn't it?
The draft has described a general use case and described 3 specific use cases, but they are all just informative.
Yeah, I know that, but you couldn't just come up, when you do this, you just couldn't come up with a new use case without documenting it in a draft.
If you have another use case, I would assume there will be another draft.
Exactly. That's what I'm saying. I'm saying somebody couldn't just come up with their own undocumented use case for these derived PCs. Okay.
Yeah.
Any further questions? Okay, thank you. We're coming up to our last presentation. Kaliraj.
Hi, Jeff. Can you hear me?
Loud and clear. Please continue.
Okay. Hi, everyone. This is just kind of a repeat of the presentation that we had in the interim. We were discussing about next hops, and this is a proposal that tries to unify the way we carry next hops and BGP for various purposes. Next slide, please. So we will go through, we will rush to the presentation because it's discussed in detail in the interim, and here we just wanted to refresh, and we may not have much time. So we'll go through the background problem statement and the layout of the multi-next hop attribute, propagation scope, error handling, etc. And while discussing that, we will discuss the use cases in line. Next slide, please. So looking at the background, it's about thinking about how do we express next hops in BGP. So basically, what is a next hop? It's instructions on how to forward a payload specified in a BGP NLRI. So even today, we have discussed about different applications of next hops in the various presentations. And we see that the next hop information that we use today in various BGP families, it's extracted from different portions of the BGP PDU or BGP route. They can be largely classified into where to forward to. So this is like either the mandatory next hop attribute or the MP reach NLRI, or the redirect to IP extended community, tunnel encapsulation attribute, color only community, redirect to VRF extended community. And we see some new attributes coming in for the meta TLV kind of a proposal. And then what kind of encap to use? Either it's a label or a prefix SID, SRv6, or any new encap that may come in future. And then the constraints. That's what kind of mapping community or color community to use to reach the endpoint, what kind of traffic engineer path to use, and link bandwidth community, which says what is the kind of UCMP we want to the next hops. Next slide, please. So that was the information that we carry on one route. And then how do we express multiplicity? We just, we advertise multiple routes, either with from different peers, or if it is from the same peer, we use add path to advertise multiple paths. And each one of those routes have its own next hops. And this has worked so far. And there is some increased RIB scale, specifically RIB out scale implications for it. And another thing is like for all the different mechanisms that have been specified in the previous slide, AdPath really caters to the next hop and MP reach attribute, where the next hop is carried in those attributes. For all the other ways how next hop is carried, AdPath is kind of unspecified, the procedures. It may work or it may not work. And then how do we, when we receive all these routes, then we do multipath or protection based on the local config. So as a whole, how we gather the information that's required to program the fib or consume and program the forwarding, it's like organically grown, and it's in different portions of the BGP route and in local configuration. So all of this has to be consumed together by an implementation, and then it has everything that it needs to do the path selection and program the route. Next slide, please. So is there a problem with this? So we see that so we have the signaling coming on the route and the local configuration in combination, giving an implementation what it needs to program the fib. So it has, this mechanism has the inability to, first of all, advertise more than one next hop in a route. And it is not expressive in the sense that the advertiser can control the fib by installing routes with next hops which have various relationships. So even if we are able to advertise multiple next hops in AdPath, we are not able to express the relationship between the different next hops. And it's not easily extensible for newer endpoint types, encapsulation types, etc. So if we had these properties, maybe we may be able to use BGP as an API, as a standard API to the receiver's fib for different type of payloads. And also, if we have a uniform way of expressing the tunnel, the encapsulation info for different address families, like SAFI1 cannot carry labels today, then we will be able to make the core simpler. We don't need service routes in the core. Service routes can be close to the edge, and that will be extending the principles of a BGP free core. Next slide, please. Yeah, so in some cases, we want to advertise multiple labels, and that helps in the label oscillation avoidance. And in some other cases, the semantics of a downstream allocated label, if it is known by the receiver, they may be able to visualize the network better, or they may be able to do EP decisions better. And then there is a problem slightly unrelated to the next hop level scope. It's at the route level, where if it's an option C domain, we don't have local preference like control for it today. Because local preference is, though it seems like it's intended to and it designed for use in a single domain, which is like a single AS or a configuration. And option C domain, though it is a single administrative domain, but we don't use local preference for it because it is going over a eBGP session, and BGP doesn't have a way of identifying which set of ASs is part of that domain. So there is a risk of leaking that to outside outside the domain. So we don't allow local preference today. So the lack of scoping control of attribute advertisement with option C domain scope. So that is another problem. So these are the problems that are attempted to be solved by the multi-next hop attribute. So let's see the layout, how it works. Next slide, please. So it's an optional non-transitive attribute, and its usage is also negotiated with a new BGP capability. And it's a TLVI's format, which is extensible for newer endpoint types, encapsulation types, forwarding actions, and argument types. And it can carry one or more next hop instructions. And it can basically be used as a API to a BGP-based API to the receiver's FIP. Next slide, please. So this is the bird's eye view of the attribute itself. Basically, the multi-next hop attribute, it has a propagation scope checker, and then it has one or more MNS TLVs. And each TLV, it has a type, and it has a next hop forwarding information. And the next hop forwarding information itself is one or more forwarding instructions. And the forwarding instruction is a forwarding action and forwarding arguments. So forwarding action is things like forward, pop, push, swap. And the forwarding arguments are like, what are the arguments that you require to complete that action? Like where to forward to, what kind of encapsulation to be used. So if you think about it, so today whatever we have is the next hop is the forwarding instruction, and this is and that is applicable for IP routes. For MPLS upstream allocated labels that cannot be used because we don't have a way to specify pop, swap, push as part of the next hop. Whatever labels that we receive as a next hop or in the NLRA 8277 encoding, that is used as a push. So for that, the action is implicitly push. So those forwarding actions, they are just enumerated here. And the propagation scope checker is what allows restricting the propagation scope of the attribute so that we can realize the domain local preference kind of functionality. Next slide, please. So initially, this attribute was transitive, and after the discussions, we made it non-transitive. And it also carries the advertising protocol next hop, which can be used to know if the MNH is valid, whether it was added by the router who rewrote the next hop. So because it's made non-transitive and it is also negotiated, the capability is negotiated in the open message, the question that comes is, do we need this anymore? Maybe because it is more, the propagation scope is more conservative now. I'm wondering whether we can remove the advertising PNH portion from the attribute. So that's one question that comes after doing a little thinking. And so even among the speakers that understand the MNH, the advertisement is controlled by this propagation scope checker. So we, by default, don't address to any BGP speakers, and we have flags that allow advertisement to IBGP confederations or eBGP. And when it is eBGP, we have a list of allowed ASs. So this is what allows constraining this advertisement within a domain. And next slide, please. So these are the types that are defined today. So type 1 is the upstream signaled primary forwarding path. Type 2 is like upstream signal backup forwarding path. So today, whatever we do with the regular next hop is type 1. You can think about it like that. And then type 4 is the domain downstream signal label descriptor. And all these about types, they have a forwarding information TLB, which will describe what is the kind of forwarding actions and arguments. And type 3 is domain local preference. So this is the type which just carries a 4-byte local preference value. And this value will be used in the path selection wherever a local preference is used. So in the option C cases where a local preference is not available, if domain local preference is available, we use this. And unknown types, they are propagated with the MNH, if the MNH is propagated. And here there are flags available at this scope. There's another question that I had, whether we need to add an indication like a partial bit, which lets a receiver to know whether a particular type has traversed to speakers which don't understand it. Next slide, please. Yeah, so this is the next hop forwarding information. This is what describes the next hop, and it contains one or more next hop leg elements, next hop forwarding instructions. Next slide, please. So this is the forwarding action, and here we see the different forwarding actions that are possible today, and some of them which may come up in future. So replicate is one example where I mean today we don't do much. Just like it's like unicast or ECMP or active backup, or you can do a replicate. So everything that's possible today is enumerated here. If a new forwarding action comes today, tomorrow we can just extend it here. And each forwarding action has one or more arguments. Next slide, please. So these are the type of endpoint identifiers that are available today. So IPv4 address, this is IPv4 next hop address or IPv6 next hop address, which identifies a node. And MPLS label, either upstream allocated or global scope, or we can say forward to a particular forwarding context at the receiving node, or a forwarding context identified by the RT at the receiving node. And even the IP address, which identifies a node, for example, when Linda was talking about the site-based forwarding, site ID-based forwarding, it occurred to me that, let's say you have this IP address. Today, an IP address, what we have here is identifies a node. But let's say we have a different scope where we say we send this information, send this traffic to a site. And there we have an IP address that identifies a site, not a particular device. So we could have a different type here where we say this is a different type of identifier. It does not identify a node, but it identifies a site. So it's just extensible in a way for future. Next slide, please. And this is the proximity. I mean, these are the different path constraints argument TLVs. One of them is proximity check, which can enable the sender to say whether this next hop should be restricted to be single hop, or it should be expected to be multi-hop. Or if both of these bits are clear, then it'll take EBGP single hop and IBGP is multi-hop, just like what it is today. And other constraints like the transport class ID, that's a color, or the load balance factor. So different constraints can be given. And these constraints will just qualify the endpoint that has been communicated with. Next slide, please. Yeah, so these are the payload encapsulation info signaling TLV. So it enumerates the different encapsulations that we have today, common ones, the MPLS label info. And so the things like ELC capability or other capabilities of MPLS related capabilities are encoded along with this MPLS label info. So just that the information is like scoped closer to where it belongs. And then the others are like SR MPLS index, label index, and SRv6 SID. And in addition to encapsulation info, for every endpoint, what are the attributes that the endpoint has, either available bandwidth or something else that may want to advertise in future. Next slide, please. So as we see that each forwarding instruction has a forwarding action TLV and a set of arguments. So each forwarding action can specify this is the minimum set of arguments that is required. And we see that this mechanism is like very flexible. So, but it carries the information closely scoped so that we can set rules based on forwarding action, which are the minimum set of arguments that needs to be there so that the forwarding information is valid, and the rules based on that. So generally the error handling mechanism is followed in this draft is like attribute discard approach. So try to deal gracefully with the errors as much as possible, and unknown TLVs are ignored and propagated. And if there are TLVs which are received and they are not able to be processed, log it with enough diagnostic data. And worst case, keep the attributed discard mode and don't use it. For example, because we are able to advertise multiple next hops in a single route. So if a receiver is not able to uh, process that many next hops based on the kind of ECMP he supports, so you can just assume that uh, the whole attribute is in discard. So it's a more conservative approach that is currently specified in the draft. We could say that okay, you can install whatever ECMP depth that you can, and so those are the things that we need to discuss. There are more details about error handling in section 6. So yeah. So with this, that's the end of the presentation. Keyur, you had a question?
Hey, Keyur Patel, Arcus, I got a number of comments. I can send this out to you, but I think typically when we have an invalid next stop, we take the path out of the best path, right? Today. So attribute discard might be just a little too gentle. You might just want to consider taking the path out completely if this is going to be a preferred method. Then my second comment is you called this as a next hop attribute, but really this is actually, the more you start to think about it, packing attributes for a given next stop, and you can carry multiple next stops now in a single update message is what you're trying to do. So you may want to have a better naming. And last thing I had was you said it's non-transitive, but you probably want to consider making it transitive if you're going to carry local pref and other such attributes across EBGP boundaries.
Yeah, so sorry, what was the first question? First one was about your first comment was,
I can send you all those things.
yeah. So basically, if you think about it, today we have the next hop attribute, right, which is mandatory. And when we carry the MNH, so that next hop will also be there in this. So about the validation of the reachability of the next hop endpoints, IGP cost, all those things will be calculated for all these next hops as well, because all of these are also next hops. And if you have a different type of endpoint and which has reachability propagated via a different mechanism, then that will specify how to calculate those equivalent IGP cost or reachability verification. And if none of the legs are reachable, then this attribute is not usable. And then the BGP route will also be unusable, because that will mean that the next hop address carried in the actual next hop attribute is also unusable. I hope that answers the first question. And about the second one was about, transitive, non-transitive, right? So we just wanted to be conservative in the sense that, so the whole idea is about being conservative so that the attribute never leaks out into the internet. So that is why we wanted to have it as non-transitive, though it may be a hurdle for the initial implementation, where we may not have all the RRs or ASBRs implemented this feature. But once we cross that, then I think it will be for the longer, if you take a longer view, it'll be safer to have it have that confidence that it's not going to leak into the internet ever. So that's why it was kept as non-transitive.
Anything else, Garrett? Thanks, Garrett. So this is less addressed to Kalyaraj and more addressed to the working group. I would encourage everybody to take a look at this draft, even if this doesn't seem to be something you're specifically interested in, because we're hitting a theme within IDR, as Sue had in the chair slide, about what do we do about carrying next hops and forwarding information within BGP PDUs as a general topic. So Kalyaraj's draft does a nice job of sort of summarizing things like scope, propagation, tying forwarding behaviors to it, and let's call them security properties of these sort of things. We see a little bit of theme of this also inside of the BGP CAR proposal with the optional NRI, trying to bind that to the individual destinations. As Kalyaraj points out, there's other proposals like things we do in FlowSpec. And outside of BGP, those of you who've done work, for example, in Google's gRIBI interface, they recognize the next hop groups for their programming looks a little bit like some of what Kalyaraj is doing for multi-next hop here in BGP. So as a side effect, we're entering a space where we're looking to see what do we want to actually carry in BGP for this information, and do we continue encoding this as small incremental changes to the BGP update that we have today, or do we start looking at what basically the update format is for our future extensions? We do have a question at the microphone.
Yep, I'm Swadesh from Cisco. I think we should define the scope, because as we see today, BGP carry a next hop, and now it's a proposal to carry a multiple next hops. It impacts BGP best path, how paths are invalidated. In general BGP, I'm not sure how we are going towards it. This draft doesn't clarify any of those stuff at all. And BGP packing, we are carrying a label, forwarding info, encapsulation, everything in attribute. And it's proposed it will be carried with BGP, all the SAFIs. So whatever we have developed for 10 years, 15 years, it will impact badly. So badly, I'm saying the word. So, and UCMP today, if I have two such paths, how will I invalidate? I have 4 next hop in one path, 4 next hop in another path. How will I do tracking, invalidation? So I'm not sure. We should be looking this with more concern than if it is I think scope has to be defined before we even move ahead with any such thing.
So as much as Kalyaraj would like to give you time to respond to that, and so we're going to give Jeff like a minute at the microphone. We are at the end of our session and we are over time. So Jeff, please keep it quick.
Yeah, pretty much to support. The complexity is non-trivial. It changes a lot of stuff in BGP. I can imagine it will take multiple years to validate such image with such functionality. I mean, it's becoming completely non-human readable after these changes, right?
So let's please have this discussion on the mailing list. There's a lot of good content here. And again, we're looking at what do we do in the future, even if it isn't necessarily what's in this draft, but this draft is a good place to start having the discussion. IDR, thank you for this session. We will see you at IETF 116.
Thank you.
If you haven't scanned the QR code to sign in, that's our blue sheets. You want to make sure there's space in the room. Scan the code. Hi. How goes? It becomes now a little simple.